Pluto, the baffling bantam planet living at the outer edges of our solar system, is stirring excitement within the cosmic community. Ongoing reports indicate a potential encounter with Neptune, raising concerns among researchers and space enthusiasts alike. Prestigious specialists, including Neil deGrasse Tyson and Michio Kaku, have sounded alarms about the possible consequences of this celestial conflict. Pluto was subsequently reclassified as a bantam, or dwarf, planet due to its unique orbit. Regardless of this change, it continues to captivate and engage space experts. Ongoing predictions from prominent researchers highlight a troubling closeness between Pluto's orbit and that of Neptune. These specialists warn of a possible impact between the two planets, posing a significant theoretical threat even to Earth. Pluto's journey around the Sun is marked by extraordinary characteristics. Its orbit spans an impressive 248 years, and since its discovery in 1930, Pluto still hasn't completed a full revolution, adding to its mystique. The unusually elongated shape of its orbit deviates from the nearly circular paths of the major planets. Moreover, Pluto's orbit is tilted 17 degrees to the ecliptic plane, making its path steeper compared to others. One of the most intriguing features of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, defying expectations based on their positions in the solar system. The answer lies in gravitational forces exerted by other planets. The analysis of Pluto's orbit began shortly after its discovery and presented a formidable challenge for astronomers. Unlike most planets whose orbits lie close to the ecliptic plane, Pluto's steep inclination and eccentric orbit make it unique. The mystery deepened with the realization that Pluto's orbit crosses Neptune's. The stability of Pluto's orbit amid these complexities is a testament to the intricacies of space mechanics. The three-body problem in astrophysics involves calculating the motion and gravitational interactions among three celestial bodies such as Pluto, Neptune, and the Sun. This problem explains the complex interchanges of their paths and forces. Terms like IML, libration, and the Kozai sway help unravel this celestial mystery. Astrophysicists argue that a kind of orbital vibration responsible for maintaining planetary positions plays a key role in the Pluto-Neptune system. This libration ensures that when Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune, crucially preventing crashes. Libration further ensures that when Pluto nears Neptune or other gas giants, it stays predominantly above their orbital plane, offering an extra layer of protection. The Kozai sway explains why Pluto's orbit appears irregular but remains stable over time. Despite apparent randomness, mathematical simulations from the late 1980s revealed that Pluto's orbit, though seemingly steady, is chaotic. Even minor deviations can lead to dramatic changes over millions of years. However, this chaotic behavior still preserves long-term orbital stability, keeping disorder within limits. Ongoing simulations have enhanced our understanding of how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path. Neptune completes 3 orbits for every 2 of Pluto's resonance that contributes to Pluto's stability. Jupiter's immense gravity exerts a strong influence, and even Saturn plays a role. Through extensive studies, researchers have shown that the combined gravitational effects of Neptune, Jupiter, and Saturn ensure Pluto's safe and stable movement through space for billions of years. These stabilizing mechanisms are vital for maintaining the order of our solar system. Without them, chaos could reign, possibly leading to impacts or orbital ejections. Understanding Pluto's orbit is crucial in discussions about a potential future collision with Neptune. It highlights how seemingly unstable paths can find equilibrium through gravitational dynamics. Continuous observation and investigation are essential for better understanding our place in the universe. Exploring space often reveals the capricious nature of celestial bodies. Pluto's orbit is a prime example of such eccentricity. The concept of orbital chaos underscores how a celestial body's path depends heavily on its initial conditions. Even small changes in Pluto's position or speed can significantly alter its long-term trajectory. Simulations in the 1980s uncovered another curious aspect. Despite forces like libration contributing to Pluto's stability, its orbit can still display irregularity. A slight initial difference can lead to major changes in its orbit over time. Nevertheless, Pluto's orbit remains stable over billions of years, suggesting an underlying order beneath the chaos. Predicting the future paths of celestial bodies with complex orbits like Pluto's is extremely difficult. These systems are inherently unpredictable. While mathematical simulations help us forecast planetary motions, they also expose the limits of our predictions. Even a tiny error in initial conditions can result in vastly different outcomes. The chaotic nature of Pluto's orbit serves as a reminder of our universe's ever-changing complexity. While we've made progress in understanding space, Pluto continues to expose the limits of our knowledge. Gravitational influences from massive planets provide valuable insight into broader solar system dynamics. Despite these insights, leading astrophysicists remain concerned about a potential Pluto-Neptune collision. Neil deGrasse Tyson, a renowned astrophysicist, offers a unique perspective. Famous for reclassifying Pluto as a dwarf planet, Tyson views this not as a demotion, but as a necessary update in light of advancing science. He emphasizes the evolving nature of celestial mechanics and believes the complexities of Pluto's orbit offer rich opportunities for discovery. Tyson also understands how space events capture the public's imagination. He sees Pluto's reclassification and its strange orbit as chances to ignite curiosity and deepen public engagement with science. Along with other researchers, Tyson warns about the potential risks of Pluto's chaotic trajectory. After extensive studies, he has voiced concerns that the three-body problem may one day lead to a long-overdue collision with Neptune. Such an impact could disrupt the balance of the solar system and unleash consequences that extend even to Earth. A Pluto-Neptune collision would be rare and catastrophic. The crash would release massive energy, likely destroying Pluto and scattering debris across the solar system. This debris could pose risks to other planets and moons. Neptune's atmosphere or orbit might also be affected, depending on the collision's dynamics. Michio Kaku, a renowned theoretical physicist known for his work in string theory, provides additional perspective. Kaku views Pluto's orbit as a window into the future of space exploration. Understanding these complex gravitational interactions, he argues, is critical for navigating the solar system and planning future missions. He also emphasizes the connection between celestial mechanics and theoretical physics. The gravitational dance between Pluto and Neptune, Kaku suggests, is tied to fundamental physical laws. Studying such interactions could yield insights into the workings of the universe at its most basic level. If Pluto and Neptune were to collide, the event would be a once-in-a-lifetime observational opportunity, potentially contributing to our understanding of string theory. This framework, which replaces point-like particles with vibrating strings, aims to explain all fundamental forces and matter. The extreme conditions of such a collision could help test its predictions, especially related to gravity and spacetime. While a direct impact on Earth would be negligible due to our distance from the outer solar system, the scientific implications could be profound. Gravitational waves from the impact, for example, could provide critical data about the structure of space. Pluto's orbit, balancing stability and chaos, demonstrates the dynamic nature of celestial mechanics. The forces that shape its path are subtle yet powerful. The universe holds countless secrets, and the three-body problem is only one of them. Other systems, like TRAPPIST-1 with its 7 Earth-sized planets, also face the threat of instability due to orbital resonances. These resonances, while creating order, can also destabilize planetary systems over time.